Salutations! Today we're going to look at implicit differentiation, which is another tool that we can use to take derivatives. So we know that the derivative of a function gives us the slope of the tangent line. But what about graphs that aren't given by functions? Right? For example, what about the graph x squared plus y squared equals 25? What shape is that going to give us? Hopefully you know that equation gives us the graph of a circle. It looks like this. It's got center at the origin and radius 5. I haven't labeled my axes, just want to get a very brief glimpse of what these look like. So here we have a shape, and we very well might want to know what the slopes of the tangent lines are going to be at different points. Right? And of course, any point on this circle is going to have a tangent line. So we want a method that's going to work here. And there is technically a way that we could do this, but it's a little bit annoying. If we wanted to solve for y in terms of x, we could do that, but there's one thing that's a little bit tricky here. If we subtract x squared from both sides, that gives us y squared equals 25 minus x squared. And then if we want to get y alone, we have to take the square root of both sides, but we need a plus or minus symbol. And the reason we need the plus or minus is because the plus refers to the top half of the circle, and the minus refers to the bottom half. So we would have to split this up into two different functions, right? This does not pass the vertical line test. So this is not a function. We would have to split it up into two functions and deal with those separately, and that's a bit tedious. But also there are other graphs where we can't easily do that, or we might not be able to do that at all. All right, here we have another graph, and this is actually called the folium of Descartes, and this comes from the equation x cubed plus y cubed equals 6xy. Now, this isn't a function. We can't look at this with y as a function of x, because if we look at some vertical lines, they actually intersect this in 3 different points. So we couldn't even just break this up into 2 functions, like we split the circle into the top and the bottom. We'd have to deal with 3 functions here for certain parts, and I honestly don't even know if there's a simple way to break this up and write these as nice functions. So I'm not sure if we could even do that if we wanted to, but we don't want to write this as 3 different functions. We've got a nice equation that represents it, so there should hopefully be a way that we can differentiate this to get the derivative at any point on that curve, and then that would figure out the slope of the tangent line. And there is a way that we can do this. It's called implicit differentiation. Now, when we're dealing with implicit differentiation, we're dealing with an equation that has x and y in it instead of a function that's just y in terms of x. So it's a little bit different, and there's a couple of steps that we have when we're doing implicit differentiation. Now, the first step is to differentiate both sides of the equation with respect to x. We've done a lot of things in algebra where you do the same thing to both sides of an equation. You might add or subtract the same number to both sides of an equation. You might multiply both sides of an equation or divide both sides of an equation by the same number. You might square both sides of an equation or take the square root of both sides. There's a lot of different situations where we've done the same thing to both sides of an equation, and then we've had a resulting equation that we could continue working with. And the same thing is going to be true here. We can take an equation with x and y in it, and we can differentiate both sides of the equation. And that's going to give us another equation that's true. But there's something unique that happens here. All right, I want to look first at x squared plus y squared equals 25. All right, before we even talk about step 2, let's consider x squared plus y squared equals 25. Now, I said the first step is to differentiate both sides with respect to x. Now here's the thing. If we want to differentiate x squared with respect to x, what is the derivative of x squared? Well, it's just 2x. Plus, we have to consider the derivative here of y squared. Now, here's the thing. Y is not x. We need to figure out how we're going to deal with y. Now, we know y is not a constant. So we're not just going to say that the derivative is 0. If it was a constant squared, then it would be 0, but this is y. But we can't just say 2y, because that would be the derivative of this with respect to y. We are differentiating with respect to x. So what we need to do is we need to recognize that even though y is not a function of x, we are hoping to consider it that way. Whenever we're looking at any given point, when we want to find the slope, we want to find dy over dx. We want to think about y as a function of x. And so this is actually a composition of functions where the outer function is y squared and the inner function is y as a function of x. We can't write it as a function of x with an explicit formula, but we're considering it to be a function of x. So when we differentiate this using the chain rule, the derivative of y squared is 2y times the derivative of the inner function with respect to x, because remember, we're differentiating with respect to x, is dy over dx, or we could write y prime. Truly, either one is fine. Let's do dy over dx for this first one, and then maybe we'll jump to y prime in the future. So that's what happens on the left-hand side. The derivative of x squared with respect to x is 2x, and then the derivative of y squared with respect to x is 2y times dy over dx. Students always have a hard time understanding this or thinking about why this is true. Remember, we're considering this a composition of functions because we're thinking of y as a function of x. Wherever we're zooming in, wherever we're looking at a tangent line, we're thinking about how y changes with respect to x. So we've got to have the derivative of y with respect to x, and that's just dy over dx. Now on the right-hand side, if we differentiate with respect to x, the derivative of a constant with respect to x is just 0. So the right-hand side is going to be 0. And now we have an equation that relates x, y, and dy over dx, the derivative. And our second step is to solve that equation for either y prime or dy over dx. Same, right? We want to get this dy over dx alone. So we can subtract 2x from both sides to move that term over. This gives us 2y times dy over dx equals negative 2x. And then to get that dy over dx alone, we need to divide both sides by 2y to get rid of the 2y on the left. And that leaves us with dy over dx on the left. And then the 2's cancel on the right, and we just have negative x over y. And so this is the derivative of y with respect to x for that equation. Now, this looks just a little bit different from a derivative we've seen before, specifically because when we look at this derivative, it's not a function of x. This derivative has x and y in it. And the reason for that is because if we're looking at this circle and we want to know the slope of the tangent line, knowing the x-coordinate isn't enough because there are oftentimes 2 points with the same x-coordinate, and those points have different tangent lines with different slopes. So when we're using implicit differentiation, it's quite possible, and honestly it's likely, that the result that we get is going to be in terms of both x and y. Now, I want to do one more thing about this circle before we finish this video and get into example problems. I want us to actually find the equation of one of the tangent lines. Find an equation of the tangent line to this curve, x squared plus y squared equals 25, at the point 3, 4. So we have the derivative here. We know that y prime, I'm switching notation just so we get used to both. Y prime is negative x over y. Now at this point, y prime at the point 3, 4 is going to be equal to negative 3/4. So we know the slope is negative 3/4. We also have the coordinates of the point, so we can use point slopes form. Y minus y1 equals m times x minus x1. That's going to be y minus 4 equals negative 3/4 times x minus 3. And if we want to get that into slope-intercept form, we can distribute that negative 3/4. Y minus 4 equals negative 3/4 x plus 9/4. And then to get y alone, we need to add 4 on both sides. That gives us y equals negative 3/4 x plus, we've got 9/4 plus 4 more. That's 16/4, and that gives us 25/4, it looks like. So we've got y equals negative 3/4 x plus 25/4. If you go through the example problems, you'll get a lot more practice dealing with implicit differentiation. But practice aside, hopefully you can see how useful implicit differentiation is for us as a tool. It allows us to find slopes of tangent lines and derivatives in general for equations with x and y that can't be expressed easily as functions. Right? There's a lot of shapes that we might deal with that can't easily be expressed as functions. Specifically, I'm thinking circles, ellipses, hyperbolas, a lot of those conic sections, and then other interesting shapes like the folium of Descartes. And so being able to use implicit differentiation does open some doors for us for dealing with other shapes.